Hello, and welcome back to the exploration of space. We're moving right along as we go from Unit 1 of your text, the Introduction of Space Exploration, to Unit 2, Orbits and Trajectories, with our focus today on understanding orbits. Earlier in this course, we talked about where space fits into our lives, how we explore space, and the environment we find in space. Now, we'll learn about the motion of objects in space. Previously, we talked about the space mission architecture as a collection of orbits and trajectories, spacecraft, launch vehicles, and missions operations systems. These building blocks of a space mission represent the interrelated elements required to make a space mission successful. Well, that's the big picture. Today, we'll narrow our focus and concentrate on orbits and trajectories. We're going to discuss orbital motion by using a baseball as a model. We'll also talk about how we analyze orbit motion. By the end of this lesson, you'll know the definition of an orbit. You'll understand how an object is put into orbit, and you'll be able to explain the steps in the motion analysis process. You should be aware that the material in this section is the basis for all other orbital motion topics in the course. So, what does that mean to you? It means that you have to pay special attention to all the material and make sure that you understand the concepts. Be sure to study the text and illustrations carefully in order to reinforce our discussion today. Let's take a minute and go back to some previous information that has a direct bearing on this material. Do you remember what we discussed about gravity? Aristotle insisted that heavier objects fall faster than lighter objects. But Galileo tested this theory and discovered that all objects fall at the same rate in the absence of atmospheric drag. So, what does this have to do with spacecraft? Well, you should begin to think about some interesting questions. Does gravity act on objects in motion the same way? You can see where we're going with this. Now, we'll start using baseballs as the example. Imagine there are two baseball players. At exactly the same time, the player on the left will drop a ball from a set height, while the player on the right will throw the ball horizontally from the same height. Which ball should hit the ground first? You're right. Both balls should hit the ground at the same time because Earth's gravity is acting on both of them equally, pulling them toward Earth. Let's look at this from another perspective. Imagine you're this player standing on top of Pikes Peak in Colorado throwing baseballs. If you throw the baseball sort of fast, what'll happen? Right, it'll fall to the ground a short distance from you on the side of the mountain, like the lower ball in the figure. If you throw the ball faster, it'll go further and fall to the side of the mountain again, like the middle ball in the figure. Well, given a perfect Earth, if you throw the ball just fast enough, it'll fall all the way around the Earth and hit you in the back of the head. Guess what? This baseball is now in orbit. In order to be in a circular orbit, the baseball has to have the right horizontal speed or velocity so gravity can actually pull it all the way around Earth. So, if baseballs or spacecraft are thrown fast enough, they will miss the Earth and, ideally, stay in orbit. That's exactly what happens with spacecraft. Now, let's talk about this figure. The shape of the Earth is such that the surface falls away 5 meters for every 8 kilometers you go out on the horizon. We know that gravity will pull the baseball towards the center of the Earth. And we know from the last slide that if we throw the ball just fast enough, it'll fall around the Earth. It turns out that we'd have to throw the ball at about 17,600 miles per hour in order to have it stay in orbit near the surface of Earth. Ideally, at this speed, the baseball would never hit the ground, as long as there's no air resistance. How fast do aircraft travel? They travel about 700 to 800 miles per hour, not fast enough to stay in orbit. Spacecraft need rockets and launch vehicles to get them to the right velocity so they can fall around the Earth in orbit. Now, let's continue with the baseball example. If this pitcher throws the ball fast enough to cover exactly 8 kilometers in the time it takes the ball to fall 5 meters, it will be in a circular orbit. If the ball is thrown a little slower, it's in an elliptical orbit that actually hits the Earth. This is what happens with an intercontinental ballistic missile, or ICBM. If we throw the ball faster than we did for the circular orbit, it's in a bigger elliptical orbit. If we throw the ball faster still, it could attain a parabolic orbit and actually escape from Earth. And when we throw the ball super fast, it escapes and could go to another planet. So, spacecraft are like baseballs in that if we give them the right velocity, they can remain in orbit, falling around Earth or escape to other planets. Okay, now that you understand how a spacecraft remains in orbit, let's talk about how we can analyze and predict the motion of satellites. A very handy tool has been developed that allows us to pinpoint the motion of spacecraft. We call this checklist the Motion Analysis Process. The process has 6 steps as listed here. First, we have to define a frame of reference or coordinate system. That means the motion is described with respect to some location, like the 0 point in this figure. The coordinate frame shown here has 2 dimensions represented by x and y. Using this coordinate frame, we can measure how far the baseball travels in the x and y directions as it moves in its trajectory. For spacecraft orbits, we use a 3-dimensional coordinate system with the 0 point at the center of the Earth. Next, we need a simple way to describe the motion and its relation to the forces involved. We would use an equation or equation of motion to describe what's happening. Often, these equations are a little complicated, so we try to make them easier by making some simplifying assumptions. For example, we could assume that the force of atmospheric drag on the baseball is so very small that we do not need to include it. Or if we want our spacecraft to orbit Earth, we can assume that the pull of gravity from Venus would have too small an influence, so we wouldn't worry about it. With these simplifying assumptions, we could calculate that the only real influence on the baseball and spacecraft is the pull of Earth's gravity. Now we can make our calculations even more useful by assigning some initial conditions. This just means that we carefully define how and where the motion of the baseball begins. In our figure, we could say that the baseball was going a certain speed at the 0 point. We also considered different situations. For example, suppose the baseball was going faster than we thought at the 0 point, causing the ball's motion to change. Or we could have put a spin on the baseball that would change its motion. These are examples of error analysis. The error analysis allows us to figure out what small changes in our initial conditions will do to the baseball's trajectory. Our last step is to actually put the equation to the test. We would test our equation of motion or model by throwing some baseballs and measuring their actual motion. We'd then compare the actual baseball trajectory to the answer we got with our equation. If the model matches the actual trajectory, we have a good model. But if it does not, we need to improve or change our model. This same process is used to determine orbits and trajectories of spacecraft. How do you think engineers perform this test, especially when they have to find errors before the spacecraft is launched? If you said by computer modeling, simulation, and hands-on testing, you'd be right. We're able to find the errors and fix them when we test the model. Once all the errors have been identified, we may have to change the coordinate system, the equation of motion, the assumptions, or the initial conditions. Tweaking the motion of the spacecraft by using the motion analysis process will help us have a successful mission. The activity questions pretty much sum up the information in this lesson. Make sure you understand all the concepts, and if you're having trouble, ask your teacher for help. Remember, this material is especially important because you have to understand it in order to successfully proceed to other topics. In this clip, you'll see several baseballs thrown at different velocities from one altitude. I want you to notice that several baseballs are not going fast enough to reach orbit, so they fall partially around the Earth and then hit the Earth. They are examples of ICBM trajectories. Pay particular attention to the baseball that remains in a circular orbit. It has the right horizontal velocity to remain in orbit, so we threw the baseball at just the right speed. Lastly, notice that there is a baseball in an elliptical, bigger orbit than the circular orbit. This baseball was thrown even faster than the ball in the circular orbit. Okay, today we covered some basic concepts we'll need when we discuss orbits in more detail. By understanding the force of gravity, you can understand, predict, and explain the motion of nearly all objects in space, from baseballs to ICBMs to satellites and even to planets. You also know the basic tools for analyzing orbits called the motion analysis process. So, let's see what comes next. We'll keep the motion analysis process in mind while we learn about Newton's laws of motion. Once we understand the laws of motion, we can use them to explain the motion of the heavens, the paths of the stars, and Earth's future positions. See you next time.